The next thing we want to do with induction is use induction to prove formulas about recursive functions. So we first have to talk about what is a recursive function. A recursive function is a function that is defined in terms of itself. Let's see an example of that. So here we have a function for every non-negative integer n. So this function is only defined for non-negative integers. Let f of n equal the following. If n is equal to 0, then f of n is 2. Otherwise, if n is greater than 0, then f of n is equal to f of n minus 1 plus 10. That's the definition of this function f. Notice that the definition of f relies on f itself. So f is defined in terms of itself. So f is a recursive function. For those of you who have learned about recursion in programming, it's the same kind of thing, right? And you can even write a method or a function in a programming language called f, which computes exactly this. It takes a number, and if the number is 0, then it returns 2. And if the number is greater than 0, it calls itself recursively, right? The function calls itself recursively to compute f of n minus 1 and adds 10 to that and returns the result. So this is an example of a recursive function. Let's just see how we can use a recursive function. So what is f of 4, for example? All right. So usually when you have a function and you want to know what is f of 4, you just plug 4 into the function. But here it's not so simple because it's a recursive function. So let's see, f of 4, well, let's follow the definition of f. Here again, we're given the definition of f. So f of 4, well, we know that f of n is equal to f of n minus 1 plus 10. Well, first of all, 4 is greater than 0. So we're going to have to use this second case. And we're supposed to say f of n minus 1 plus 10. Well, n minus 1 would be 4 minus 1. So that would be f of 3 plus 10. But what is f of 3? I don't know. So we have to figure that out. Right? So if we're trying to figure out now f of 3, well, now we're doing f of 3. So n is equal to 3. So what would that be? Well, f of 3 would be f of 2 plus 10. So what we have is f of 2 plus 10. So again, f of 3 becomes f of 2 plus 10. Again, this is based on the definition of the function. And then we still have this plus 10 from the previous line, which we keep. Now, what is f of 2? Well, once again, we have to use the definition of f. So now n is equal to 2. So f of n, f of 2 should be f of 1 plus 10. So f of 2, okay, will become f of 1 plus 10. And then, of course, we have the plus 10 from before, which we keep. Now, we still have more work to do because what is f of 1? I don't know. Well, let's follow the definition of the function. F of 1 should be f of 0 plus 10. So f of 1 over here will become f of 0 plus 10. And then we have still the plus 10 plus 10 plus 10, bring it down. Now, f of 0, that is simple to figure out because we are told in the definition of the function that f of n is equal to 2 if n is equal to 0. So here we have a case where n is equal to 0. We want to know what is f of 0? Well, that's simple. It's just 2. So now we have 2 and then plus these 4 10s from before. Now it's just simple addition, add them up, we get 42. So, but notice how much work it took just to figure out f of 4. And of course, if we would want to figure out f of 14 or f of 54, it would take a lot more steps. So the question is there a simple formula for f of n that works for every integer n that is greater than or equal to 0? Right? Again, the function is only defined for integers that are greater than or equal to 0. So we don't care about negative numbers because the function is not even defined for them. But we're just considering non-negative integers. Is there a formula, a simple formula that doesn't require so many steps for f of n? So instead of using this definition, can I redefine this in a simpler way? That's the question. Well, we're going to see that the answer is yes, and we're going to see how to prove that answer. But before that, let's just do another example of a recursive function. Okay, so this was a function f. Now let's do another function which we'll call g. which is defined as follows. For every non-negative integer n, let g of n equal to 3 if n is equal to 0. Otherwise, if n is greater than 0, then g of n is 5 times g of n minus 1 plus 2. Notice again, the definition of g relies on g itself. So g is a recursive function. Because in other words, in order to figure out g of n, I have to compute 5 times g of n minus 1 plus 2. So the point is, to compute g, I have to use g itself. Let's get a little practice with this function, get a feel for what it does. So what is g of 3? Well, g of 3, following the definition of the function, should be, well, g of n. So n is greater than 0, right? 3 is greater than 0. So we have 5 times g of 2, g of 2, yes, n minus 1, g of 2 plus 2. So 5 times g of 2 plus 2. But what is g of 2? Well, again, we have to use the definition of the function. So g of 2 would be, well, n is equal to 2 now. So that would be 5 times g of 1 plus 2. So g of 2 will become 5 times g of 1 plus 2. And then we have to multiply it by 5 because we have this 5 times g of 2. So it's 5 times this, and then plus 2 from before. But now we're not yet done, because what is g of 1? Well, following the definition of g, that should be 5 times g of 0 plus 2. So what do we have? Well, g of 1 becomes g of 0, 5 times g of 0 plus 2. All right, so we have 5 times g of 0 plus 2. Now that we have to multiply g of 1 by 5 and add 2, so that's 5 times this plus 2. And then, of course, we have to add 2 because of this, right? So again, we have 5 times this plus 2, and then hold on. Sorry, let me redo that. G of 1 is equal to 5 times g of 0 plus 2. Okay, but now we have to do 5 times g of 1 plus 2, so that's this. That's all this. That's 5 times g of 1 plus 2. And then we still have the 5 multiple at the beginning and the plus 2 at the end. Now, what is g of 0? Well, that is simple. G of 0 is 3. So we get this, and then we just have to do the multiplication and addition. So we have to do 5 times 3 plus 2. So that would be 17. So now we have to do 5 times 17 plus 2. That is 87. Now we have to do 5 times 87 plus 2. That is 437. And again, we can ask, is there a simple formula for g that works for every integer n that is greater than or equal to 0? So we had 2 examples of recursive functions. We had f and we had g, and in both cases, we would like to have a simpler formula. So let's go back to f, and let's prove a formula for f. So again, this was f. This is the definition of f. We don't need to prove this. This is just given to us. We are told that this is the definition of f. Here's a proposition, though. Proposition: for every integer n that is greater than or equal to 0, f of n equals 10n plus 2, 10 times n plus 2. Notice, this is not a recursive formula. In other words, to find f of n, I just plug in 10 times n plus 2. Very simple. Like to find f of 4, it would just be 10 times 4 plus 2, 42. Right? So this is a very nice formula. Now, how did you come up with such a formula? We're not going to cover that in this course. It is a nice topic to study, but we're not going to do it in this course. It's often covered in analysis of algorithms. At any rate, we want to prove this formula. We want to prove that this formula is correct. So again, we're given this definition, f of n equals this. We don't need to prove it because it's given to us. That's just how f is defined. We want to know, is this formula equivalent to f? In other words, will this formula always give the same answers as the actual function? Will it always produce the same output? So given any random input, will it always produce the same output as the actual function itself? So that's what we want to prove. We want to prove that this formula works. In other words, we want to prove that this shortcut works. So here's going to be a proof, and we're going to use induction. So we have the basis step. Now, the basis step here is going to be when n is equal to 0, because we're talking about integers that are greater than or equal to 0. So when n is equal to 0, well, let's see what does the definition of the function say? Well, when n is equal to 0, the definition of the function says that f of n, which is equal to f of 0, is equal to 2. Now, this agrees with the formula, because what does the formula say? 10n plus 2. Well, that would be 10 times 0 plus 2, which is 0 plus 2, which is 2. So notice, so again, the point is in the case when n is equal to 0, the definition of the function agrees with the shortcut, with the formula. So that's the basis step. That's the easy part. Now we have the hard part, the inductive step. What do we need to do here? We need to show that for every integer k that is greater than or equal to 0, if f of k equals 10k plus 2, meaning if the formula works for f of k, then it has to work for k plus 1. Then f of k plus 1 equals 10 times k plus 1 plus 2. So again, we're trying to prove that if the formula works for k, so meaning if f of k is equal to 10k plus 2, then the formula works for f of k plus 1. So that's what we want to do. That's what we want to prove. So we're going to, since we're proving an if-then, we're allowed to assume that this part is true, right? So suppose that f of k is equal to 10k plus 2. Our goal will be to show that f of k plus 1 is equal to 10 times k plus 1 plus 2. Okay, so again, suppose that f of k is equal to 10k plus 2. Then what is f of k plus 1? Well, let's see. We have this definition that we can use. Remember, the definition is given to us, so we can use it. What is f of k plus 1 based on the definition of f? So think about it. If we take k plus 1 and plug it in as n, what does the definition of f give me? Well, that would be f of k plus 1 minus 1. That, in other words, f of k, and then plus 10. So f of k plus 1, based on the definition of f, from the definition of f itself, is equal to f of k plus 10. Again, f of n is equal to f of n minus 1 plus 10. Well, what about if n happens to be k plus 1? Right? What happens if n happens to be k plus 1? Well, then it's going to be k plus 1 minus 1, which is f of k, and then plus 10. Right? Again, f of k plus 1 minus 1, which is f of k, plus 10. So that's f of k plus 10. That's from the definition of f. Okay, but now what can we say about this? Well, we are working under the assumption that f of k is equal to 10k plus 2. So we can rewrite it as this, 10k plus 2, and then plus 10. And this comes from the assumption about f of k. Then we can factor out a 10. 10 times k plus 1, right? So then that's 10k, and then that's another 10. So that's 10 times k plus 1, and then, of course, plus 2, which is exactly what we wanted to show. We wanted to show that f of k plus 1 is equal to this, right? F of k plus 1 is equal to this. So we have proved that this formula is correct. In other words, we have proved that f of n is always equal to 10n plus 2. When n is n is greater than or equal to 0, then f of n is equal to this. We have proven that. Let's now do the same thing for function g. So here was function g was defined like this. Again, this is the definition. We're not trying to prove it. We're taking this as given because it is given to us. That's just the definition of g. Here's what we want to prove about g. So here's a nice formula that does not involve recursion for g, right? So the formula says for every integer n that is greater than or equal to 0, g of n is equal to 7 times 5n minus 1 all divided by 2. Now, how did someone come up with this formula? Well, there is a way, but we're not going to cover that. If you want to look this topic up and learn more about it, that would be would probably be under something called recurrence relations, or it might be called the master theorem. That's another keyword that you might want to use, but recurrence relations is probably the topic that you might want to look up if you're interested in seeing how to come up with these formulas in the first place. At any rate, we're not worried about that. We just want to prove that this formula is correct. In other words, I want to prove that this formula here actually agrees with this function in all cases. So we're going to use induction. And the basis step is when n is equal to 0. So what does the formula give us when n is equal to 0? Well, that's 7 times 5 to the power of n minus 1 divided by 2. So that's 7 times 5 to the 0 minus 1 divided by 2, which is, so 7 times 5 to the 0, this is 5 to the 0 is 1. So that's 7 times 1 minus 1, that's 6 divided by 2, which is 3. Now this happens to align with g of 0. It agrees with g of 0. In other words, so when n is equal to 0, we have that the formula that we're trying to prove agrees with the definition of g, because the definition of g says that when n is equal to 0, in other words, g of 0 is equal to 3. So they agree. So that's the basis step. Inductive step, what we need to do is we need to show that for every integer k that is greater than or equal to 0, if g of k equals 7 times 5 to the k minus 1 divided by 2, meaning if the formula works for g of k, then I want to show that it has to work for g of k plus 1. Then g of k plus 1 should be equal to 7 times 5 to the power of k plus 1 minus 1 divided by 2. So you want to prove this. So suppose that g of k is equal to 7 times 5 to the k minus 1 divided by 2. Well, then what can we say about g of k plus 1? Well, then g of k plus 1 will be equal to, well, follow the definition of g. G of n is 5 times g of n minus 1 plus 2. So in the case where n is equal to k plus 1, what does g of n minus 1 become? Well, it becomes g of k plus 1 minus 1. In other words, g of k. So in sum, when we have g of k plus 1, that should be 5 times g of k plus 2. Again, that comes from the definition of g, which was given to us. We don't need to prove anything about that. That's just a fact given to us. All right, but now we are working under the assumption that g of k is equal to 7 times 5 to the k minus 1 divided by 2. So we can replace this with this fraction. Okay, like this. All right, now what I want to do next, well, I have to keep in mind my goal. My goal is to show that g of k plus 1 is equal to this fraction, right? So I have g of k plus 1, and I want it to be equal to one big fraction like this. So I want to combine all this into one fraction. Well, the 5, this is 5. So what am I going to do with it? Well, I will multiply it by 7 times 5k, and I'll also multiply it by -1. So that's 5 times 7 times 5 to the k, and then it's minus 5. And then as for this 2, well, I want to make this one big fraction here, right? So what I'm going to do is find the common denominator, which in this case would be 2. So in other words, I have 4 over 2. So what I have so far is 5 times 7 times 5 to the k minus 5, all divided by 2, plus 4 over 2. Again, how did I get this part? Well, this thing here, this is a 5, so it's really like 5 over 1. So what I want to do is multiply the 5 by this, and then multiply the 5 by -1. So that leaves me with this. Okay, now let's simplify the fraction. So we have 5 times 7 times 5 to the k minus 5 plus 4, all divided by 2. Now, what can we do with this? Well, what we have here, if you can rearrange the 5 and the 7, right? So it's really 7 times 5 to the k. What is 5 times 5 to the k? So really this is 5 to the 1 times 5 to the k. Well, that becomes 5 to the k plus 1. So this becomes 7 times 5 to the k plus 1 minus 1, because the minus 5 plus 4 becomes minus 1. And then it's all divided by 2. And that's exactly what we wanted to show. We wanted to show that g of k plus 1 is 7 times 5 to the k plus 1 minus 1, all divided by 2. And we've done that. So we have completed the inductive step and the basis step. So the induction proof is complete.